Hello, my name is Ian Barnes. This is my physics lab 5. So, in this experiment, I'll evaluate the human rocket where Felix Baumgartner jumped out a balloon from 38,969.4 meters above Earth. And in this lab, I want to determine Felix's final speed when he pulled his parachute using the energy principle and how high you would have to jump to break the speed of sound. I'm also going to look to see if the energy principle is upheld by modeling his free fall and closed curve compared to the calculations. So, for the setup of this lab, my system is Felix, Earth in the air, and I have no surroundings. And in this jump, he tries to break the sound barrier. We know that using the energy in the system, it is conserved due to the principle of conservation of energy, but we're looking to see if our model follows that with the kinetic and potential energy in the system change. And then in the closed group model, to represent our system, I have the initial position at 0 in the x component, 38,969 in the y component, and 0 in the z component, and then initial velocity is 0 across. So the principles I used were Newton's second law, where F equals ma, and then the net force is just the gravitational force, and then I have the position update and velocity update, gravitational potential energy, which is mgh, kinetic, which is 1 half mv squared, and then the energy principle, where change in energy is equal to q, which is the change in heat, and work plus work. And since Earth and air are already included in our system, there's no work from surroundings. So the statistics needed for computations are the jump altitude, which I've said before, the final descent, where he parachuted the final 2,566.7 meters. So that means the free fall distance was 36,402.6 meters. And the top speed he reached was 843.6 miles per hour. So, and he also had 4 minutes and 20 seconds of free fall, and he was supersonic, or he was at the speed of sound for 30 seconds. The speed of sound is 343 meters per second, and the weight of Felix, including the suit, was 118 kilograms. So the calculations, considering the jump height of 38,969.4 meters and the height that Felix pulled his parachute, we know he dove for 36,402.6 meters. Now, applying the energy principle, we can see that when his parachute was pulled, Felix was traveling at 845.1 meters per second by just comparing the initial and final energies and making them equal to each other. And then the other calculation I did was that if he wants to break the sound barrier, what velocity would he need to reach? So again, I made the energies equal to each other and solved for h using the speed of sound, and I got 5,996.4 meters, but Felix also needs to parachute down to the ground safely, so you'd have to add that distance of when he was parachuted, which was 2,566.7 meters. So if he wants to break the speed of sound, he would have to jump from 8,563.1 meters. So in the glow script code, I first initialized the graph plotting and the mass of Felix, which I represented him as a ball, which is just 118 kilograms. Then I initialized the height jump and the velocity. I also defined the energies and gravity. And then in the time loop, I used the time of Felix's flight of 260 seconds and the net force, and I also did the velocity position and update formula. And then I stopped the graphs at 0, and I calculated the energies and I plotted them on the graph. And then here are the graphs that GlowScript gave me, where you can see position inverse time and velocity. Velocity is negative because in this experiment up is considered positive, and it shows that Felix reaches 845.1 meters per second at the end. So, and then here are my energy graphs, and you can see that kinetic and potential energy are inversely related. So if we were to add these together, it would be a straight line across 0. So the conservation of energy is upheld. And then some possible errors in the experiment could be that in this experiment I said that the system was isolated, but in reality there is work on the system due to outside forces like air resistance and wind. And then in the glow script model, I said that Felix was considered as a ball, technically a point, which is very inaccurate considering he would actually have drag from air resistance, and that Felix flew straight down with no displacement in the x direction. However, he would have moved horizontally as well due to outside forces. And then the questions I wanted to ask were, how does terminal velocity come into play if air resistance was considered? And that terminal velocity happens when a freely falling object experiences 0 net force. So that would mean that the drag force from air resistance would have to equal the force of gravity. To have this happen, Felix would likely have to spread out his arms and legs to increase the surface area of the suit of himself. So the force of drag increase to equal the force of gravity, and that would stop Felix from continuously accelerating. And then another question was, what if Felix jumped without a suit? We would have less mass. How would that impact the time of free fall? So if Felix jumped without a suit, he would have less mass as the suit weighed around 70 pounds or 31.75 kilograms. And while that reduction in mass would lower Felix's weight, this wouldn't change his time of free fall. In the absence of air resistance, the time of free fall primarily depends on the height and gravity, as you can see in the formula to the bottom right. And thank you.